Thank you. So this is a little bit different. We're not talking about a particular deployment. We're talking about something that impacts all of the deployments. So there was a number of requested changes that came across. My name's Edwin Buck. I'm uh, basically a data engineer with Hewlett Packard, and I'm a product expert in a couple of products, including SPIRE. And Bloomberg came with a particular request because they saw a problem inside their deployments where the database utilization was very high. And so special thanks to them for effectively funding the changes that you're about to see. Everybody is probably somewhat aware of what a SPIRE entry is, unless you're not yet using SPIRE. A SPIRE entry is effectively the database and configuration elements that are used to receive a request for a new SVID. And then depending upon how the entry is configured, the SPIRE server may send SVID back or may not. And one of these things with this mapping of like configuration elements requests is that there's an intense amount of lookup that happens internally inside the SPIRE servers. They're constantly being asked to check their SPIRE entry database. This presents a problem that had been solved in the past through what is a full cache of all of the database entries. Because the database entries, which are normally stored in a relational database, would be pulled out so frequently. The SPIRE designers had basically decided to create an in-memory cache of all of the SPIRE entries. Now, this assists in a couple of ways. One of the ways is that when you're standing up multiple SPIRE servers, now you can just have all of the SPIRE servers refer to the same database and use it as a coordination point. Any SPIRE server or SPIRE executables that wants to insert an entry will insert it into the database, and then it'll be distributed out to all the SPIRE servers. One of the side effects of keeping those entries into all the SPIRE servers is that all of those servers will have to refresh their cache of the entries from the database. And the initial approach was, a simple approach. There were many other tasks that SPIRE had to do. And the simple approach was just basically load the entire database every 5 seconds. This process was called hydration, and it involves throwing the cache away and reloading it. So this concept of constantly loading the entire cache from the database and then discarding the entire cache from the database, and then loading the entire cache from the database and discarding the entire cache from the database, it's very CPU intensive, it's very network intensive, but you usually don't feel these kinds of pain points until you have an installation that grows to a very large number of SPIRE entries. So it was sort of something that everybody kind of wanted to fix at some point in time, but until you had enough of the larger installations complaining about it and causing performance issues it wasn't going to get fixed. So what we did is we needed a new approach. And the new approach involved actually taking the cache and instead of rebuilding it from scratch, just simply pulling for updates and pulling the changes into the cache. And this concept of pulling for updates and pulling the changes into the cache meant that unless you were literally getting rid of every one of your SPIRE entries and then recreating them all, you were going to get fewer updates than you would the entire cache. And so this would reduce the amount of transmitted entries across the network. And if you structure the database schema correctly, it should also reduce the amount of work the database engine would have to do to return the changed items. So one of the problems with trying to pull for these updates is how do you make sure that the database doesn't have to do the same table scans it would have to do on all entries in order to get the updated ones? And we came up with a design for what we call database events. And this is a separate table in the database. that basically indicates which entries have been manipulated and is saved simultaneously with the entry that is being manipulated. So we still have the entry inside the entries for all of those who are familiar with that table, and it's still updated there, which means that like on startup, we still load that table in full, and we don't have to change like all of the SPIRE logic. But when it's time to consider updating a cache, we just simply read the entry events, and the entry events give us the indications of like which lines that hold an entry inside the cache need to be evicted and updated. When we set this up, then there became new questions, which was, how do we ensure that all the servers see these? So we had to make sure that that some of our roll forward logic was actually outside of this experimental event, because it is an experimental configuration at this point in time. You have to turn it on. And we ran into a few issues where some of the non-enabled SPIRE servers were not writing the entries, and then the enabled SPIRE servers would miss any updates that happened on those servers. Since then, we have moved the logic that is required for this experimental feature outside of the experimental area. So all of the servers will write the entry events table. So if you turn this on, you will guarantee to have, even just for one or two servers, as long as they're all on 1.9, they will pick up the entry events regardless of where you update them. Another thing that you sort of need to consider is that since we now have this entry events table that holds that this entry has been changed or that entry has been changed, that's a table that will always grow. Even if you change the entry like 5 times, you expect 5 entries in that table, and without some sort of pruning or vacuuming of that table, it will just grow for forever. So there is a prune events older than configuration item, where you can basically say that, if the event is older than an hour, or you're pulling that table every 15 minutes, then, the event will fall off the end of the table. One of the features of this experimental change is that these entries are not processed twice. So you basically have an insurance that, like, if you prune an old event, as long as it's not set faster than the polling time, which, would be very hard to set it faster than the polling time, then you basically should not miss any events. Okay, so this is the problem and this is the solution that we approached. And then, of course, no solution is actually useful unless you validate the solution. And so we started benchmarking the solution. We picked some really underpowered hardware because we wanted to top out the database as quickly as possible. And if you put a big beefy server on it, it takes even more entries to do so. Basically, we collected it with a custom purpose-built benchmarking suite. For all of these benchmarks, we're going to be measuring CPU on the database processes of Postgres, and lower values are better here. Now, one thing that you'll notice in the data is that the values are rather spiky, okay? But these spikes that you see, just slightly before 2140 on the left chart and just before, say, 1233 on the right chart, those spikes represent internal Postgres processes that wake up every now and then and do things like table vacuuming and memory restructuring and, scanning for freeing the information that is no longer needed for the query processing engine. What we are actually interested in are these really low blue ticks that are near the baseline. And that's because that represents the actual amount of overhead that the database has to sustain due to the frequency of the polling. And so over here, you can see that both of the tables at like 100 SPIRE entries, basically, it doesn't really matter which database system you're looking at. They're both being impacted very little because 100 entries is really fast to query out of the database. When you bump it up to the next power of 10, there's still not very much difference. 1,000 entries between the two measurements. Yeah, there is a little bit of a difference in the polling frequency because we have stronger guarantees in not missing records, so we're not polling the events as quickly. But generally speaking, the performance almost the same. When we start getting to 10,000 entries, you'll notice that the baseline starts lifting on the system on the left, which is the system that has the old logic in it. And this is because every 5 seconds, it's pulling all 10,000 entries across. This involves having to do internal memory allocations, paging inside of Postgres, marshaling of the items onto the wire. And then, of course, the unpacking of that, which happens in SPIRE, is not part of these benchmarks, but SPIRE itself will also see a small amount of processing because it has to unpack these items. Whereas on the left, since we're only really looking at the differential of how many changed entries, effectively the baseline stays very close to what it was before. Bumping it up to 100,000 entries, it's now quite noticeable. The database, performance on one system is, easily measurable in load. And this is part of the reason why Bloomberg took particular attention to this performance issue. They actually are monitoring their database performance as an early indicator of database failure and system administration needs. So, with an active monitoring system, you can't have a database that just constantly looks like it's on the verge of, not operating efficiently. On the right, you'll notice that the spikes seem to be higher, but that's only aberration due to the scaling of the graph. In reality, that's 2,000 marks, which is the same marks that it was in the slides before. So if you go back to the slide on the left, that would be effectively about the height of the green line below. And when we get to 1 million entries, we finally get so high that the responses start washing from one of our polling cycles inside the benchmarking into the other because the response cannot be fully processed within the 1 second time capture that we're using on this platform. Granted, this is a lower power platform in order to exasperate the problems of the response times. But on the right, you can see that, we still remain at about the, 2,000 CPU operations. So generally, we found that the time to create the cache didn't change because when you start up the system, it's the same system. It still has to load the entire cache. We're not actually saying that we're not going to have a cache inside SPIRE. The cache is really a benefit for speedy processing of SVID requests, and it's almost become an inherent design feature of SPIRE. But the time to update the cache, it changed in big O performance from an ON algorithm of demands on the database to an O1 algorithm on demands on the database. And, there are some caveats on this O1. Clearly, it's not O1 based off of every possible thing that you could imagine. The O1 is tied to the number of database changes. It just, it's no longer the big O performance is tied to the number of database changes. It's no longer tied to the actual size of the database. So if you sit there and you have like a cycle where you are making, 10,000 database changes, then you'll see a blip, but that blip will eventually fall off of your entry table, and then you'll go back down to having almost no processing at all. So for this, basically, you know, when we took a look at all the features, there's still a few areas where we could perform some extra improvements, although some of these areas are sort of like lesser importance because the main problem of using the database CPU inefficiently has been solved. And right now we've got a couple of entries in the backlog. We'll take a look at, you know, if and when we need to pursue any of these performance improvements. Some of them are icing on the cake, and quite honestly, some of the work that was recently done over at Uber fleshed out more important things than performance improvements, such as small code cases where various portions of the cache were not being updated for one reason or another. So the entire project was deemed a massive success by Bloomberg and HPE, and by pretty much anybody who wants to use it. I highly suggest that if you wish to use this, that you get all of your servers on 1.9, and then you enable the experimental features to turn on the database events. If you don't wish to use this as an experimental feature, I believe that this has had a significant enough impact on processing of entries in SPIRE that it will probably be lined up for the 1.10 release. But that's in the future, so, you know, future doesn't come with guarantees. And were there any questions?
Thanks so much, Ed. I think there were a couple of questions. What size are we talking about? What are the number of workload nodes we're talking about here? I don't know at which point, Eli, you were asking that.
So this is an unusual
at the beginning.
Yeah, this is an unusual performance issue because the building of the cache really does not get impacted very heavily by the number of workloads or the number of nodes. It's really a function of the number of cache entries, the SPIRE entries. And the reason why is because, like, while all of the workloads would eventually necessitate a cache hit, that cache hit really doesn't have anything to do with the database performance because it's already inside the in-memory cache. The goals here were to reduce the load on the database systems, because when you start attaching many SPIRE servers to the same database as our current deployment architecture requires, then you wind up having all of those SPIRE servers competing with the database resources in the database as far as CPU in order to send back all of those cache entries every 5 seconds. So the main idea here is that we didn't bother to benchmark for the workloads because the cache hits are an independent measurement of the goal of getting the database performance down. Does that make sense?
Is it like for one database instance? So I'm a little bit confused because usually you run like multiple instances and then everything like goes across of them. I'm curious because it's been like, I don't know,
So the server
4
deployment,
years.
the server deployment right now recommends a single database engine or a pool of replicated database engines, which they will talk about the replication without actual support for it. It's just up to the organization to implement its own replication approach, depending upon which database that they pick. But the point is that you are configured to, for most systems, a single database engine. And then inside that database, it may share schemas, but all of the deployments that I've been doing, I've been recommending an independent schema for SPIRE only inside one engine. It just makes it a little bit easier to manage, and it goes with an easier deployment and removal process, or if you need it. Does that help you a little bit, Eli?
A little bit, Eli. Let me look at some other questions very quickly. Probably I missed, but it is eventually consistent with events. Dimitri, I know you have a couple of questions if you want to unmute and ask them.
Yeah. Yeah, so one of them, like, I just maybe missed this part, like, but when you say you added events, like, is it added some eventual consistency in system, or you still have absolutely guarantees that it's up to date, you never lose any information?
Ed?
Sorry, I didn't hear that because I was trying to answer a question in chat. Could you repeat the question, please?
Okay, so my question is mostly like, when you say like you added eventual consistency for cache or events, like, do you mean that in some states it's actually not exactly like ACID and we have some mismatch, let's say, with cache and database, or you guarantee that never happens such mismatch?
Well, the eventual consistency is very similar to the eventual consistency that it had before. When one of the servers would put an entry into the database, an updated entry into the database, it would take about 5 seconds for all of the other servers to be guaranteed to have read it. And that meant that there was a small window of time between, 0 and 5 seconds where the servers might actually have differences inside their caches because none of those servers would be synchronized to read them at exactly the same time. But that was never really an operational issue because there are locks around the cache to make sure that when you don't have a fully loaded cache, you're not using it. So from each server's point of view, you would just generally, not process any of the event, potential SVID matching while the cache was being rebuilt from full. Now that you're basically rebuilding it by removing and evicting cache lines and replacing them with the newer information, we've kept the same locking mechanism around the cache during this process. So there is not really a point where you would get, say, half of the cache updates for a 5-second cycle. And the 5-second cycle was so short in time that we did not see any kind of, race conditions
Okay.
between the agents, because the agents connect only to one server. So from their point of view, they just got the information that they got from the server. If another agent happens to read the cache like 2 seconds earlier and got a different answer, well, those answers are also typically very specific to the agent. So it's not like the agent over here on node A, which cannot issue this SVID because of the way that the entries are structured, is going to somehow notice that, the agent on node B that is the only agent that issues this SVID, somehow had the wrong idea of what the cache line was 2 seconds before, the agent that really doesn't even get to be aware of that. There's a lot of filtering that occurs. These entries are pushed out to the agents, and the agents have their own internal caches, and that will help the agent filter some of the requests to decide whether or not it needs to, say, reissue request an SVID issuance from the server. But the timings that are involved and the locking that's around it means that while if you had like some sort of global clock and you could perfectly understand the state of everything, none of these things are really coordinating in a way to where you have that diamond pattern and the changes come back to one element that then suddenly has like well, what happened, it was there and now it isn't kind of problem. Does that make sense?
Yep, thank you.
Yep. I also see a question about the benchmarks, saying that there's a limit of the entry event count when compared to the total cache size. So the total cache size in this is not a limited cache. This is a complete copy. of the events as rendered from the database queries into what we call a cache. So if you're thinking about like a cache that has a limit and certain lines are evicted based off of lack of space, that's not the functionality that occurs here. What occurs is effectively it's a cached copy of the entire set of entries inside the database. And so when we're talking about the event count, well, the event count primarily is the most obvious variable that would determine how long it would take to build this cache from nothing. So the two algorithms that are there, one that consistently builds the cache from nothing, and one that only updates the portions of a pre-existing cache with the items that need to be updated. You know, you can really see huge differences in performance here. But it's not like you would have a cache miss ever. If it's not inside this cache, it's not inside the database, and it's not configured to have a SVID response. Does that help you a bit, Marco?
Yeah, thank you.
All right.